Kinetics Example 14. The decomposition of N2O5 in the gas VSAs was studied at constant temperature. This is the reaction we get. The following results were collected. So data was collected. You should have already graphed this. Okay, but here's the data, the time versus concentration. You need to graph ln versus concentration and inverse concentration to figure out what order it is, or to verify that it's first order. So just as a reminder, you'd have to graph concentration versus time, calculate, or you have the computer calculate the natural log of concentration versus time for us, and then you'd have a third column where you do the inverse concentration versus time as a third column. Once you do that, you will see that the most linear plot is when you graph ln of concentration versus time. Here's something like what your Google Sheet should have looked like. So this is concentration versus time, 0 order, natural log of concentration versus time, first order, and inverse concentration versus time, second order. You can see the most linear plot is first order, so therefore that's how we verify it. So from the video, from the assignment, you were able to make the plots on that Google Sheet, and you would then write this statement to support answering question A. First order as a linear plot for natural log of concentration versus time. If this was 0 order, you'd say 0 order as a linear plot for concentration versus time, and if it was second order, you would say second order as a linear plot for inverse concentration versus time. However, this is first order, so we would say first order as a linear plot for natural log of concentration versus time. Part B has lots of stuff that we're looking at here. We're looking for the K from the graph, so we're going to use the fact that we know it's first order, so we're using this right here. And we know slope. When we figure out the slope, we know K because we take the opposite sign of the slope from a graph to get K. Now, the important piece here is that you know what graph to make. So let's look at that. Or I apologize for what data you're pulling to calculate the slope for. It must be the slope of the straight line. So that's when you would do time versus natural log of concentration. We're going to use this slope equals y2 minus y1 over x2 minus x1. And let me explain a bit further. So we know it's first order. So we know from that chart I just stepped away from, slope is equal to the opposite sign of k. So then we know k is equal to this. Now let's see how we did that. So remember, making this xy determination has to be not of concentration, because that didn't give us the linear plot, and inverse concentration didn't give us linear plot. What gave us the most linear plot was when we graphed time versus natural log versus concentration. That must be the graph for which you calculate the slope from. I picked 2 points arbitrarily. I just picked 50 and 100. Didn't want to deal with 0. So I make time my x, natural log of concentration my y. Therefore I did 0.2, which was -3 minus -2.66. So y2 minus y1. And then 100 minus 50, x2 minus x1. Get this answer. I find that the slope is -6.80, but based on the chart, we know that if we know the first order slope is opposite sign of k, or k is the opposite sign of slope, however you want to think of it. By the way, you should have positive values of k. You will not have negative values of k. So therefore, this is our k. We will use that k throughout the rest of this example. Okay, here we brought our k over. It says using k, find the time it would take to decrease the concentration to 0.0356. Remember, it's first order, so we're looking for time. So we can't use, that's not going to help us. This doesn't have time in it. There's a time in here. This is half-life, so we wouldn't use this, and we're not going to plot anything, so that time is useless. So we're, once again, looking at this middle group right here. This is the most common column in this formula chart you will use. And we're going to take the natural log of the initial concentration over final concentration equals K times T. Okay, so here is that formula. The natural log of A naught over A equals KT. If you just jot this down and you're not listening through what I'm doing, you're going to be lost on these problems. So please do not be tempted to just write everything down and go. It will make it a lot more difficult to get through these when you're doing them on your own. So we have time versus concentration. And I realize that we went back to time versus concentration. That's because we're dealing with concentration now. We already know the order. We don't need to worry about the ln or the inverse concentration any longer. So we're looking to see, when does this When does this concentration fall into play here for us to know what this is like? So let me give you just a moment. I want to fix my screen here. So we're looking for time. So if we're looking for t here, we have k, so we know that. And now we're looking for which of these is the unknown. Well, we can't have t as an unknown. That's what we're solving for, and both of these be an unknown. We were given a concentration, and we wanted to decrease to this concentration. So this is going to be our A, our later, because it's going to decrease to this. So this is our later or final concentration. That's going to go down here with the A. We need an A naught. So I got to figure out where does this fit in my concentrations, assuming that they're following a pattern as they are here. You see that it's decreasing. So it's going to fit right here in between 0.05, 0.0356 will fit between 0.05 and 0.025. So now I have 3 initial concentrations I can use corresponding to 3 different times. So let's look and see what I chose. I chose the one right before it. Okay, that's fine. You could choose any of these. It would just change this part in blue a little bit in a moment. So I chose 0.05. So I can crank this into my calculator and I get 0.0500 divided by 0.0356. I get 1.404. If I take the natural log, I can put this into my calculator. I don't have to do any e things like we did before. I'm going to take the natural log because it's just a number, and I can crank that on my calculator. I get 0.399. I can divide that by my k, and I get a time of 49.90 hours. Now, this is how much time it takes for it to go for here. But we know already that 100 hours have passed. To get to 0.05, 100 hours passed already. It took 49 hours to go from this concentration to the 0.0356. So we have to add the time that's already passed, 100 hours, to the time it takes to get this portion, the 49.90, and that's how I get 149.9. So if you would have picked initial concentration of 0.1, you would have gotten 149.9 here, or very close to that. Same thing. So you got to add the time that's passed already to the time you get when you're doing it in the middle of a time frame. Okay, example D, it says calculate the rate of reaction when N2O2i's concentration is this. So we're looking for rate. So we're still first order, and the only place that we have rate is this first column. So rate equals K times concentration. So our K from the previous calculation is here, times our concentration, multiply those numbers, manipulate your units, and this is what you get. Okay, part E, calculate the concentration at 250 seconds after the start of the reaction. So 250 seconds after the start of the reaction. That puts us around here. So we're trying to figure out the concentration that would be right between 200 and 300 basically. Okay, so we know we're doing a first order reaction. So we got Ln of initial concentration over final concentration equals K times T. We know our K, we know our time. And I think, let me fast forward this. Okay, I paused because I realized I didn't have my unit on here on 250 seconds. So I put 250 seconds here. This is my K. And I'm going to start with any concentration above there. I start with 0.1. I'm sorry. This question actually specifically says after the start of the reaction. So I have to start at the start of the reaction. So my initial concentration is 0.1. I'm looking for this guy down here. So I can get a numeric value, right? Now, I have an unknown trapped inside my ln. If you have an unknown trapped inside an ln, you must e both sides. Take e to the x for both sides. When I e an ln, that basically makes this go away, and the piece inside drops down, so this comes down here. So e to the ln is like canceling both, and then I can take an e to this value, right? I'm going to punch this into my calculator, hit second ln, or the reciprocal of ln, so e to the x button. When I take that, I get this. You should be checking on your calculator to make sure you can get my numbers. So remember, e to the ln makes the ln both cancel. This drops down. I have to numerically get this value of 5.47. Now I'm going to put this over 1, 5.47 over 1. I'm going to cross multiply. That's how I get this. Then I'm going to divide both sides by 5.47 to get my concentration. 0.0183. So let's check and see if that makes sense. Would it make sense that 0.0183 would fit in here? Make sure that makes sense. Yes, and then it's going to go drop a little bit more and drop a little bit more. All right, on to the next example.